Hello, AP Statistics. This is a quick run-through of the 7.5 Part 1 notes for binomial distributions. You have a copy of this notes on Schoology that you can fill in, and also I believe the substitute has a print copy as well. So what I want to do is just kind of talk you through these notes, so if you have some questions, that may answer those. So first off, Section 7.5 is about a binomial experiment. A binomial experiment is a type of random variable collection, but it looks a little different than sometimes of our other probability distributions. For example, a binomial experiment looks something like this. First, there are a fixed number of trials, and each trial is independent. So for example, if I roll a die 10 times, if I draw 5 cards, if I randomly choose 20 students, suppose we choose 18 people. In all of these examples, we've chosen a fixed number of sample size, or we've completed something a fixed number of times. That is our N value, the number of trials. So if I'm going to roll the die 10 times, then my N value is 10. Draw 5 cards, N is 5. If I'm going to choose 20 students, my N value is 20. There are also, in our binomial experiment, only 2 possible outcomes of interest. Only 2 things that we think about. That's why it's called binomial, because there's only 2 outcomes. There is success and there is failure. Now, a success is the thing that we're looking for. So, for example, if I roll a die 10 times, what is the probability that I get 5 even numbers? So, for me, a success is getting an even number. If I draw 5 cards from a standard deck, what is the probability that I get 2 ace cards? So, in other words, a success is getting an ace card. So the idea with a success is that's the thing that you are looking for. So when I roll the die, if I'm looking for an even number, I don't think of the results as 1, 2, 3, 4, 5, 6. I think of them as even numbers and not even numbers, successes and failures. Or if I'm drawing a card from a deck of cards and I'm looking for an ace, I only see 2 outcomes. I either see ace or not an ace. Okay? The next variable that we want to define is the probability of success. P, lowercase p, is the probability of success, and that's how likely it is to get that success in each of your trials. So for example, back in our card problem, if I roll a die 10 times, what's the probability that I get 5 even numbers? So if success is an even number, then the probability of success, P, is 3 out of 6, or 50%. If I'm drawing 5 cards from a standard deck of cards, the probability that I get an ace, which is a success, is 4 out of the 52 cards, or about 8%. If I'm choosing randomly selected students from this college, and in this problem I've decided what's the probability that at least 5 live on campus. If live on campus is my success, then what I'm looking for is the percentage of the students that make that true. So the percentage of students who live on campus is my success rate. The other quantity of interest is the probability of failure. And since there's only 2 outcomes, that's the rest of our 100%. So if the probability of success is 50%, then the probability of failure is also 50%. If the probability of success is 0.077, so about 8%, then your probability of failure is the rest of that 100%, about 92%. If your probability of success is 60%, then your probability of failure is 40%. These two should add up to 100%. And finally, here's where our random variable comes in. A random variable, remember, it's a numeric variable, and what we're going to do is we're going to count the number of successes. Now, your number of successes can be anywhere from 0 to n, because you could never get your successful situation, or you could get as many as you had number of trials. So from no successes up to all successes. So, if I roll a die 10 times, what's the probability that I get 5 even numbers? I'm rolling the die 10 times, n is 10. I'm looking for even numbers, so a success is an even number. The probability of success is 3 out of 6, or 50%, and failure would be the other 50%. X is the number of successes I'm looking for. So if I'm looking for 5 even numbers, then X equals 5. If I draw 5 cards from a standard deck, what's the probability that I get 2 ace cards? So again, n equals 5 cards. The probability of getting an ace is 4 out of 52. Failure is the rest of that. Success, getting an ace card, the number of successes, I'm looking for 2. Out of the 5 cards, I want 2 aces. All right. In a certain college, 60% of the students live on campus. Suppose we randomly choose 20 students from this college and ask them whether or not they live on campus. What's the probability that at least 5 live on campus? All right, so I'm counting people who live on campus. That's success. I'm looking for out of 20 students. That's my in. I know 60% of them do, which means 40% of them won't. And the number of successes says at least 5. Now that means 5 or more. So basically, that means anything that's x greater than or equal to 5. In this case, since we're interviewing 20 students, that means we would have everything from 5 up to 20. X equals 5, x equals 6, x equals 7, x equals 8, etc., all the way up to 20. According to the textbook of medical physiology, 9% of the population has blood type B. Suppose we choose 18 people at random from the population and test the blood type of each. What's the probability that no more than 4 of these people have blood type B? All right, we are counting people with blood type B, which means that success is blood type B. I'm taking 18 people at random. That's my N value. I'm looking for 9% have blood type B, so the probability of success is 9%, which means the probability of failure is 91%. The rest of that, those add up to 100. The number of successes, I'm looking for no more than 4. That's not more than 4, which means it could be equal to 4 or it could be less. Now remember, these numbers are going from 0 up to n, so x less than or equal 4, you could also say x equals 0, x equals 1, x equals 2, x equals 3, x equals 4. Now, as far as probability goes, one of the most common misconceptions about binomial probability is that if I'm looking for, say, 2 successes, struggling here, having a moment of struggle, coming back. All right, if I have 2 successes out of 5, or I want no more than 4 out of 18, that we would do something simple like we did in chapter 5 or chapter 6, where we just said the probability is 2 out of 5 or 4 out of 18. And that's not exactly true, because what needs to happen is we need to first figure out where those successes could occur. So it makes a difference if the success is first or the success is second. So the order matters. The other thing we need to do is actually calculate that probability of success. So there is a formula for this, and it says the probability of x successes out of n trials, there's that variable, the number of successes out of n trials, is a combination of n choose x. Now this first little part right here, all this does is it tells us which of the trials were successes and how many ways could you do that. If I'm looking for 5 trials and I want 1 success, there's 5 different ways that that could happen. If I have 5 trials and I want 2 successes, that's more difficult. I could have the first and second, or the second and third, or the first and fourth, or etc. So this number tells us how many ways that's possible. The next says the probability of success to the x power. So if I know I'm going to have a certain number of successes, then that's the probability of that occurring that many times. And the same thing for failure, the probability of failure to the n minus x. So that's the rest. Okay? So for example, if I was going to use this formula, the probability of the situation in part A. So I am rolling a die 10 times, n equals 10. I'm looking to count even numbers, so success is an even number, and the probability of success is 50%. That means that my probability of failure is also 50%. And I want to know the probability of getting 5 even numbers. So I would plug this into my formula. Probability of 5 is 5 successes out of 10 trials, is a combination of 10 choose 5. That picks which of my 10 trials are going to be successes and tells me how many times you could actually do that. Times p, 50%, to the 5th power. There are 5 successes times 50%, that's the probability of failure, to the 10 minus 5. 10 minus 5 is also 5. So I have 5 successes and 5 failures. Okay. Once I crunch this number in my calculator, I get 0.246. Or in other words, the probability of getting 5 even numbers out of 10 rolls is not 50%, but rather it's 0.246, or about a fourth. Now you can do a combination in your calculator to manage this formula should you have to. Here from a calculator screen, those are the steps that you would follow to make that happen. All right. Now, it gets a little more complicated if you need to do more than one. So, for example, here's the blood population problem again. Blood type B, I'm going to interview 18 people. There's a 9% chance they're going to have blood type B, which is what I'm counting, which means there's a 91% chance that they won't. That's my failure rate. We were looking for no more than 4. That's X less than or equal to 4. All right, so if X is less than or equal to 4, what I would have to do to use the formula is figure out, well, that means X equals 0, X equals 1, X equals 2, X equals 3, and X equals 4. And I would have to use the formula for each of these values, which is not very much fun at all. So again, here's it plugged in. 18 choose 0, success to 0 successes, 91 to the 18 minus 0. For probability of 1, 18 choose 1. Probability of success, 9% to the first power for 1 success. And if you have 1 success, then you're going to have 17 failures. We would find the probabilities of each of these in our calculator and add them together and get the sum. That sum is our probability of getting less than or equal to 4 people with blood type B. Now, fortunately for us is that we don't necessarily have to use the formula because your calculator has a handy-dandy binomial probability calculator in it. So if you want a single value of X, I want X equals 5, X equals 4, X equals 3, one single X value. If I roll a die 10 times, what's the probability that I get 5 even numbers? Okay, success is even. I'm doing 10 trials, N equals 10. I want 5 of them, so X equals 5, probability of success 50%. You can go to your calculator, and from the menu, you just need a regular calculator screen. You're going to press statistics and go to distributions. And you're going to have to scroll down and find D. D, there are 2. Binomial PDF, that one works for a single value. And also binomial CDF, this one works for multiple values. Okay? So the difference is this one is a probability distribution. This one is a cumulative distribution. So it's going to add up a whole bunch of different ones. Okay, so once you go through these steps, you're going to get a field. It's going to give you the number of trials, the probability of success, and your X value. Once you punch that in, you will get your answer and your percentage. Same thing down here. If I want a range of X values, okay, I'm going to roll the die 10 times. What's the probability that I get no more than 4 even numbers? So a success would be even. The difference is you're going to use the cumulative density function this time, the CDF command, and it will give you the number of trials, the probability of success, etc. But it's also going to give you a lower bound and an upper bound. That's where you're going to put in your smallest X and your largest X. So the smallest that X can be is 0. That's our lower bound. And we don't want to be any bigger than 4, so 4 is my upper bound. That is the range of our X values. You punch that in, and it's going to give you out about 37% here. In our blood type example, we would enter it as N equals 18. Probability of success is 9%. Our X's go from 0 to 4, and we end up with about a 91% chance. Now, notice that this number is a little bit different to the one we got at the top of the page, and that's just due to rounding. All right. So, for example, 56% of men do not look forward to going clothes shopping for themselves. You randomly select 40 men. Find the probability that the number of men who do not look forward to going clothes shopping is exactly 25, more than 16, and between 30 and 35. Now, you notice we got a couple of typos there. You should not be surprised at this point that I have typos in my notes. So if you could fix those to be 25 and 16, that would be great. All right, first thing you're going to do is define your variable. Okay, X is a count of the number of successes out of N trials. So I'm going to put that in context. We are counting the number of men who do not look forward to going clothes shopping. So the number of men who do not like to go shopping out of our sample of 40. That's my X. I'm doing a little planning here. I know that I'm going to interview 40 men. That's my N. Success is I don't like to shop. And the probability of success is 56% because 56% of men qualify for they do not like to shop. So to get exactly 25, that means that X equals 25. X equals 25. So I'm going to put this into my calculator. This is a single value, so I'm going to find the binomial PDF function. My n is 40. Probability of success is 56%, and our x value is 25. That gives us 0.091 in the calculator, 91%. To get more than 16, that would be x is greater than 16. So that means my x is going to go from 17 up to as large as x can go. So probability of success, this is cumulative because I want more than 1, 40, 56% chance of success. The smallest number greater than 16 is 17, so that's going to be my lower bound. And the largest number of men who could say they hate shopping is 40. So this x's go from 0 to 40, and in this case, since we want the upper bound here to be 40. Punch that into your calculator and you end up with 0.969. Now, the next one says between 30 and 35. So we have to make an assumption here. Do we think this is inclusive, meaning does it include 30 and 35? Or does it not include 30 or 35? Now, on the AP test, if it didn't seem very clear in the context of the problem, you should probably assume that it is exclusive. Okay. However, if the problem seems to make sense in context that it could be inclusive, then maybe you should just say that. I assumed this was inclusive because that makes sense in context. Okay. So if you go from 30 to 35 inclusive, your lower bound will be 30 and your upper bound will be 35. But if you're not allowed to include 30 and 35, then that means you would need to have between 30 and 34. That would truly be between. A little bit of a discrepancy here by about 0.006. All right, last thing. Finding the mean of a binomial probability distribution and the standard deviation is ridiculously easy because the formula requires basically one step. All right, so the mean of a binomial distribution has this beautiful formula, which is on your formula page, and it is n times p. And this is very logical, too. For example, when Jim shoots field goals in basketball, the probability he makes a shot is only 50%. So success is making the shot. Probability of success is 50%. The mean would be the expected number. So if he's going to throw 6 times and he makes 50% of the shots, it's logical that he's going to make 3. Okay? But computationally, if you were going to do this, all you need to do is take n times p, which would be 6 times 0.5, and get that number. For the standard deviation, it's a little bit more complicated. You're going to take the square root of n times p times q. In this case, you would have to find q. Q is that probability of failure, which if p is 50%, so would q be. In pq, 6 times 0.5 times 0.5. Make sure you take the square root because 1.5 is the variance. And I end up with a standard deviation of 1.22 hits. Now, I would interpret this as the expected number of hits would be 3. We would expect Jim to hit 3 shots. And a typical deviation from that over a number of trials would be 1.22. All right, 63% of adults cannot name a U.S. Supreme Court justice. You randomly select 5 adults and ask them whether or not they can name a Supreme Court justice. Clarence Thomas. Now, let X equal the number of adults who cannot name a Supreme Court justice. So this is already defined what X is. Adults who cannot name a Supreme Court justice. So that is our success, even though that doesn't seem like a very successful thing to have happen. It is not the connotation of it. Success is literally just what we're looking for. All right, so I know that n is 5 because I'm going to talk to 5 adults. I know that 63% of adults can't. So that's my success rate. And so I could go ahead and assume right now that 37% would be failure. Now to find the mean, all I have to do is n times p. If 5 adults are interviewed, and about 63% of them are expected not to know, that gives me 3.15 adults. Okay, or about 3. Standard deviation is similar. I'm going to take the square root of n times p times q. And we end up with a variance of 1.16, which gives me a standard deviation of 1.08 adults. Similarly, if I was to be asked, what is the probability that 4 adults cannot name a Supreme Court justice? X equals 4. That's a probability. Since I'm looking for a single value, I'm going to use the PDF command. 4 adults would be one exact value. I put in my N, P, and X and bring out 29%. All right, so if you have any questions on this, I can answer them next class. Hopefully this helped a little bit if you were confused from the written notes. Please email me as well if you need any further clarification.